Welcome Bill Faris to speak to us today. Bill's from, University of Arizona, and he's going to talk about trees versus connected graphs.
Well, thank you very much. The first thing I want to do is to apologize for this talk a little bit. I had prepared a talk on some work I did recently about trees versus connected graphs, and I decided I would give a little bit of introduction, just as background and motivation for why the kind of formula that I was generating was of interest in this context. And so it turned out that when I looked at the introduction and I started to practice it, it took up the whole hour. So I'm only going to give you the introduction to my talk, and then next week I'll give you the talk. So that's the first apology. The second apology is that nothing I'm saying here is original. In fact, it's a huge part of it comes from this article by Bjorner called The Homology and Shellability of Matroids and Geometric Lattices. Now, until recently, I don't think I even would have known what the things in the title meant. I'd never heard of a matroid before 2008. So so my excuse for this talk, however, is that you might like it because it's a way of talking about these things that could be explained to an undergraduate. It has a charm to it and in fact, as I go along the talk, you can start to see some potential undergraduate projects. Things having to do with problems that physicists are concerned with, where you can actually make pretty pictures. So that's the plan, is to talk about this introductory stuff today, and then the formula that I have worked on next week. So the introductory stuff is about trees and connected graphs. So let me remind you about trees and connected graphs. So a tree, so for me a tree is always, graphs are always going to be associated with a set. So I have a set of vertices, and then a graph is a set of edges. So this is what in combinatorics is called a simple graph. For me a graph will just be specified by a set of edges. And sometimes I'll even think of the graph as being the set of edges, with the vertex set kept as a constant. And there are obviously lots of graphs because there are lots of sets of edges. 2 to the n choose 2 power graphs on a set of n vertices. And the main interest is connected graphs, and I'll say a few words about why one cares about connected graphs in a minute. There are also a huge number of connected graphs. That's a crude lower bound. And then a tree is a minimal connected graph. And here is a formula for the number of trees on a set, 2 to the n to the n minus 2 power. That's the famous theorem of Cayley. And so there are relatively few trees. So lots of connected graphs, relatively few trees. So if you take n to be 100, how many trees do you get? It's a lot. If you take n to be 10, say, let's see, 10 to the 10th. 10 to the 10th is a big number, but here, or 10 to the 8th. But if you take 10 choose 2, you're getting something that's, beyond comprehension. So the number of trees is perhaps a comprehensible number of objects, but the number of connected graphs is just huge. So now the next thing I wanted to mention is that when I'm talking about trees and graphs, I'm talking about trees and graphs on a set. Now, so for example, if we look at 3 points, there are 4 connected graphs. Here are the 4 connected graphs on 3 points. 3 of them are trees, and 1 of them is not a tree. Now notice these 3 all look the same. And so if you look at just isomorphism classes, you just have these 2 isomorphism classes of connected graphs when you have 3 vertices. So the point I'm just trying to make is that whenever I'm talking about this subject, I'm always talking about the actual graphs on the set, not about the isomorphism classes. So corresponding to this picture of the isomorphism class, there are actually these three different trees. Okay, so that's background. Sometimes I should also mention that trees are called spanning trees, is that right? And graphs are called spanning connected graphs in combinatorics, but I'm going to use this shorthand. Okay, that's going backwards. Okay. Now, the next thing I wanted to mention is that it's a property, again, that was totally new to me until actually just a few days ago when I realized how relevant it was, that every tree is close to every other tree in the following precise sense. So you take a tree T1 and another tree T2, and they're different, and so let's assume that there is an edge that's in T1 but not in T2. And the conclusion is there is an edge y that's in T2 but not in T1, such that if you take T1, take away x, and add y, you get a new tree. So trees are close to each other. Well, this is a kind of exchange property. Now, I drew a picture of it here. So the undotted lines are my tree T1, and my dotted lines are my tree T2, and I pick this edge x. So what I want to do is take away x from T1. That will give me that picture. And then I want to find a y in T2, and there may be more than one choice. So that if I add y in, I get back a tree. Did I do it wrong? Oops. Looks like that one shouldn't be there. Is it better now? It's better now. Considerably better. Much more tree-like. I'm sorry about that. Okay. So, say that again.
In this case, we will more in the bridge.
Am I in trouble already?
No, because if it's a bridge, it can't be in T1 but not T2.
Oh, yeah.
Okay.
Yeah, you are right.
You're saying
This talk was intended for the mathematical physicists, but they're all in Warwick right now. So it's a little bit hard selling this stuff to combinatorists who know it already. So anyway, this property that I just gave you of trees, this first property is an exchange property. It says that trees are close to each other. That's true for an arbitrary pair of trees. And this property has been abstracted into the concept of a matroid. So a matroid basis is a collection of subsets of some finite set. So in the example of trees, it was a set of edges with this exchange property that if x is in B1 minus B2, then there exists a y in B2 minus B1, such that if you take away x and add y, you get another basis. So it's the same property, but just stated abstractly. Instead of the word tree and edge, I'm using the word basis and this elements of this abstract set. So that's what a matroid basis is. And the nice thing about matroids is that if you look at the sets in a matroid basis, their complements also form another matroid basis. So there's this duality for matroids, which is very nice. And so here is the dualities in the case that I'm talking about. The trees form a basis of a matroid, and the complements of trees form a basis for a matroid. And the matroid itself consists of the subsets of the basis, and so the subsets of the basis in the case of trees are sets or graphs without cycles, and in the case of complements of trees, they're the complements of connected graphs. So matroids provide a setting for talking about connected graphs. So, okay, I'm not going to say anything more about matroids for a while, but I had to show that I learned something this year. Now, here's the thing I really want to talk about. I want to talk about partitioning, I want to talk about classifying connected graphs. So I look at the set of all connected graphs on a given set, and I look at the collection of all trees, and I would like to associate with every tree a collection of connected graphs in such a way that I classify all the connected graphs that way. So let's look at an example. So here are my 4 connected graphs on a 3-point set, and here are my 3 trees. And I want to use these trees to classify the connected graphs. So I'm going to use the first tree to classify itself together with this connected graph. The second tree, alas, has nothing else to classify, and the third one has nothing else to classify. So here is a partition of the set of connected graphs indexed by the trees. So the general statement is that there is a function t from trees to connected graphs such that the set of all connected graphs, oh, this should be a g sub c here, right? It's a typo, is gotten by taking the union of all these sets in the partition. And furthermore, each set in this partition has all connected graphs that are between the tree and this maximal connected graph in the partition. So in other words, if you have the tree and this maximal connected graph, then every h that's between these is a connected graph that's also in the same partition. So this partitioning of the set of connected graphs is the subject of interest, and I'll say in a minute why anyone cares about that. Okay, are we okay so far? We got the terminology and so forth straight. I haven't made any major terminology blunders. Okay. So let's do an example of a partition. Well, I guess the next slide is just giving this example. And I already explained. Okay, so here is some stuff that starts coming from statistical physics. First of all, I'd like to say something about what you want to do in statistical physics. One very standard problem in statistical physics is you have a whole bunch of particles and they interact in pairs. So you look at all pairs ij of particles, and for each pair ij you have a positive factor, which I'm going to write in this strange form 1 plus t. So that is the interaction, represents the interaction between 2 particles, and you're taking the product of over all particles. Each of these interaction factors 1 plus t is called a Boltzmann factor in physics, and it depends on some energy function and some temperature parameter and so forth. But I'm not going to write all that down because that's a whole other story. Now there's a strange thing that you can do when you write things as 1 plus t, is that you can use the distributive law. And the distributive law says the product over all pairs is given by the sum over subsets of pairs, in other words, over graphs, of the products over the graph. So that's the distributive law for distributing somethingfication over something, what is it? Multiplication over addition, I guess it is, right? The distributive law. So now the important thing is that these t's here now can be negative. So you've done a really very strange thing from a physics point of view or a probability point of view. You've taken an obviously positive quantity and you've written it as a huge sum of quantities, some of which are positive and some of which are negative.
Because 1 plus t has to be non-negative.
1 plus t has to be non-negative. In fact, it's going to be between 0 and 1, so the t itself is always going to be between -1 and 0, so each t will be negative. So these products will be either negative or positive depending on whether they're an odd number of edges or an even number of edges. Okay, so that's just to show you that this is a kind of strange mathematical transformation that's employed in physics. Now in physics, when you calculate a quantity like pressure or density or something like that, the calculation, and I in my first version of this talk, I went through the whole derivation, and that took itself a half an hour. So I'm just going to skip the physics derivation. But the point is that what you really want to do after a whole bunch of fuss in physics is, that you can find in physics books, is do the same kind of sum with these t's that can be either positive, that can be negative, and these products can either be positive or negative, where you're summing over connected graphs. So let's just take that as an axiom for the purpose of this talk, that some people care very deeply about taking the sum over all connected graphs of products of this form. Is there somebody who can witness to this so that I'm okay, all right. Now the trouble is that this sum over connected graphs is a huge sum, as we've seen, because there are many, many connected graphs. And it has, as a sum over lots of things, some of which are positive and some of which are negative. And it just looks like an impossible thing to control. But this partitioning trick helps you get back into a situation where you can start to do estimates. You can replace the sum over connected graphs by the sum over trees, because remember, the trees are parameterizing the connected graphs. And so then you pick out the edges of the trees, those factors you just take out. And now you have the sum over all the graphs in between the tree and the maximal connected graph of the edges in the corresponding edges there. And then you can undo the distributive law. And you can write that back as something positive. So now you have a tree sum, these factors which are either positive or negative, but which are this is a relatively small sum. And then you have this factor here, which could well be at most 1. So things are back under control, and the thing that made it work was this partitioning of the connected graphs in terms of the trees. Yeah.
Tij are numbers between
-1 and 0.
-1. So they are all negative.
They're all negatives.
So
Unless you're an expert, like you, and then in which case they can.
but I mean, so the sign there is the same, doesn't change.
Yeah. So the general rule is whenever I write Tij, it will always be in this range. Because the corresponding Boltzmann factor, 1 plus Tij, which is a more probabilistic quantity, is in that nice probabilistic range.
So I just want to remark that that's constant. The sign of the constant depends only on the cardinality of the set, considering the graph.
Yeah. Okay, so anyway, that means this partitioning process is an interesting process. So what I'm going to talk about next time is an alternative to this partitioning process, a way of sort of doing the partitioning sort of randomly rather than deterministically in some sense. Now, the partitioning process has the following property, and that's that it's sort of arbitrary. I associated this connected graph with T1, but not with T2 and T3. So what I want to do in the rest of the talk is explain why it's arbitrary and why there's nothing you can do about it. So that's my introductory talk. Okay, so let's see. Here's a bound that you can get from the formula I just gave. You can bound out those positive factors by 1, and you just get this huge sum over connected graphs is bounded by this relatively small sum over trees, and that's the thing that does the work in the cluster expansion and in huge number of estimates in all sorts of areas of mathematical physics. This is at least one way of seeing that you can get underway with that project. Okay, so now we go on to the kind of recreational mathematics side of things, I think. Well, we're not quite there yet. Okay, this is a remark. So I said this method, this partitioning of the set of connected graphs is arbitrary, but it turns out there's some invariance of the partition. Namely, if you look at the number of partitions of a given size, then there's a certain number of partitions that have the maximal size, a certain that have the next possible smaller size, and so on. These are the ones that have the minimal size. And you count the number of partitions of a given size and write that as a vector. It turns out that vector is independent of the method of partitioning, and it's called the H vector. So even though this partitioning seems very arbitrary, there are at least some things about it that are not completely arbitrary, namely this H vector, which is the H vector is the vector H sub I is the number of sets in the partition with 2 to the r minus I elements, where r is the, I guess in this example is this number. I'm not going to try to go through the derivation of this thing right now. It's a little piece of algebra. And we'll come back to similar things a little later in the talk. So, okay, so that was the background, trees and connected graphs, and why you care about them, their relation, about this partitioning process. What is this? The H vector. I actually worked out the H vector for for this silly example, and H0 is 1, and H1 is 2. So there's one partition with 2 elements and 2 partitions with 1 element. That's a really silly, degenerate example. Gee, I should do the example with graphs on 4 vectors. That's here, but I'll come back to that one later. So you'll see a somewhat less trivial example in a little while. Okay, so now that's the part of the talk, sort of where people are coming from in mathematical physics, why they care about this partitioning process. And now I want to talk about the thing that I learned by browsing a little bit in the library, is that you can think of these things geometrically. And this geometrical picture is just a lovely, lovely picture that just gives a whole different light on this whole story. So for this, we need the concept of a simplicial complex. So what is a simplicial complex? You have a set of vertices and then a set of subsets of the vertices, which are called the faces of the complex. And the faces are closed under, if you have a face, then anything inside the face, any subset of the face is a face. So what's going on here? Let's see if I can draw a picture that will help. Do I have any blackboard space? Yeah, I could use this here. Okay, so this is probably familiar to most people already, but just want to make sure that we're all on board. So here is a simplicial complex. Okay, so in this particular picture, I have 1, 2, 3, 4, 5 vertices. Which are these guys here. These are 1-point sets. Then I have a bunch of 2-point sets. Let's see, how many do I have? 1, 2, 3, 4, 5, 6. So 6 edges. So each, did I count wrong? 1, 2, 3, 4, see, 1, 2, 3, 4, 5, 6, 7. Yeah, 7 edges. And then I have 3, what do you call these things? Faces, triangles. 3 facets. So these all count as faces, but the highest dimension ones are called facets. So the facets have 3 points in them. The edges have 2 points. The vertices have 1 point. And I guess there's also an empty face. I mean, there has to be. So a simplicial complex is something you build up out of triangles like this. Now there's a kind of tricky point, the triangles are two-dimensional objects. These facets are two-dimensional objects in this picture, but they were determined by 3 points. And these edges or segments are one-dimensional objects, but they're determined by 2 points. So when you're talking about these things, you always have to stop and think whether you're talking about the number of points or whether you're talking that determine the thing, that span the thing, or whether you're talking about the actual geometric object. So anyway, this is a very familiar notion that anyone who's studied topology has certainly run into. So, okay. So that would be a two-dimensional simplicial complex, or a two-dimensional complex. So now let's go back to the connected graphs and think of that as a complex. So what we're going to do is we're going to look at complements of connected graphs. So if so U is the vertex set of the graph. The V, the vertex set of the complex is the edge set of the graphs. And the complex is all complements of connected graphs. So if you think of a picture like this, all of these guys would correspond to connected graphs. And the maximal ones are the maximal complements of connected graphs, which are the complements of trees. And so they would be like analogous to the facets there. So this example that we're concerned about in physics is a very special case of a simplicial complex. Does that make sense? So that ties the geometry with the things I was talking about before. Okay, so onward. Now we come to the hard part. So again, in 2008, I learned the concept of a shelling. And it's one of these definitions that's extremely simple and natural after you've read it 20 times. So a shelling of a complex is a sequence of facets. So for example, we could take this as the first facet. Then we would have to take this as the second facet. We're not allowed to take this one. We have to take one that's next to it. So that could be the second facet, and that can be the third facet. So that would be a shelling of this simplicial complex. Just a sequence of facets. However, the rule for doing it is a little bit tricky. So if we have this sequence of facets, if we look at a facet if we look at the okay, let me just do it on the picture here. So the first facet you can just put down anything you want. The second facet you get by taking an element x, not in the first facet, and joining that to the edge of the first facet. So this x is used to generate the second facet from the first facet by spanning something new and then making use of this common edge. And then to get the third facet, you have another x prime here, and you use that to build the third facet so that it has the common edge with the second facet. So that's the way the shelling works. But as you notice in this definition, there's some legal clauses. And these legal clauses I will illustrate in other examples a little bit later, but just I want to point out to you how tricky this is. So a shelling of a pure complex is a sequence of facets. So you fix a facet fj. So you're interested in a facet fj, so there's fj. And for every previous facet, there is some other previous facet and an x in fj. So here is my x in fj. here is my previous facet. So that previous facet is going to be Fk and I can build the new facet from Fk by that construction. However, I have to do it with an x that doesn't belong to my given preceding Fi. So there's this restriction. And it's just an almost impossible thing to understand this definition until you've worked with it, but I'll show you how to work with it in a few minutes in terms of examples. I mean, in that example there, you can't see the difficulty, but I'll show you in a little while some examples. So basically, the thing to remember is that there is this funny definition.
Just to be absolutely clear about the funny definition, I mean, the way you were talking a minute ago, you were saying you're going to fix a J and then have this technical small print, but you are, I presume, actually wanting this toss to go for every Fj.
Yeah, so there's an implicit universal quantifier for all j. So for all j, for all I less than j, there exists a k less than j, and there exists an x such that all these funny things happen. Okay, so it's got enough quantifiers so that it requires some thought. So let's see. Okay, so we'll come back to that definition in a few minutes. But now, once you have one of these shellings, you get a partition. And the partition is just the new stuff. So in the case of this shelling right here, the first partition consists of everything, the first facet, all the edges of the first facet, and all the vertices of the first facet, and the empty set. So everything, the first facet always has lots of stuff in the partition. The second facet has the new stuff. So it has this new edge, and this new face, and this new vertex. So the first facet, we had 8 faces associated with it in the partition. This one, we get only 4 faces. Yeah?
Yeah, I'm trying to understand the definition. So I guess it may help to think of of Fk as being somehow close to Fj. Because if you remove x
That's
from
right.
J, then you're inside Fk.
Yeah, yeah.
And then Fi is,
Yeah.
make sure is.
You're right. So Fk has to be right next to Fj.
Yeah, that's right.
Yeah. However, there can be several things next to it. And this very peculiar definition has some restrictions on which one you can use. That's the point. And I'll illustrate this with examples so it'll become clear in a few minutes. So we started out with, we have 8 faces associated with the first guy here. Then the second guy, we got a new face, 2 new edges, and a new vertex, so we got 4. This one we have a new vertex, a new face, 2 edges, so we got 4 more. So we partitioned this thing into 8 plus 4 plus 4 faces. So all the faces now are accounted for. So that's a partitioning that comes with one of these shelling sequences. And so it's basically it's the new stuff that you add.
Yeah, so basically the first condition says that the face Fj was not encountered yet, right?
Okay,
Because
so
it contains
the face Fj has not been encountered yet.
Yes.
So you want to find a Fk that's close to it.
Yeah, that's right.
So this is saying the Fk is close to the Fj.
And the first one is
But
saying-
however, for every preceding Fi, you have to have the liberty to choose your new vertex not to be in that Fi.
Yes.
It's a weird condition. Okay. Maybe somebody will help me to understand why it's natural, but I read it in the book. So, okay, now once you have a simplicial complex and a shelling, well, once you have a simplicial complex, you can write down what's called the F vector, which just counts the number of faces of each dimension. And you can also write down an H vector, which counts the number of partitions of each size. And the nice thing about a shelling is that this H vector is that this partitioning is possible So this H vector has has positive coefficients. I mean, because they're counting the sizes of something. Now that's not completely obvious because the relationship between the H vector and the F vector is that H of S, if we form a polynomial, is F of S minus 1. So this is the polynomial whose coefficients are the F vector that encodes the number of faces of each dimension. That polynomial obviously has positive coefficients. But then when you plug in this new variable, S minus 1, you get a new polynomial, and a priori it could have negative coefficients. But for a shellable complex, it always has positive coefficients, and these coefficients in fact count the sizes of these partitions. They don't exactly count the sizes of the partitions, but they count something.
Sorry, Bill, what's R of F?
What?
What's R of F?
Okay, that's R of F is the minimal, well, I probably defined it before. Let's go back. See. Did I define? Yeah.
Go back one more.
One more, yeah.
There.
So R of F is, so what it is, it's the minimal thing in the partition. So R of F, I guess here would be the empty set. Here it would be this vertex, and here it would be that vertex. The minimal new thing that's been added. So, okay. I'll give examples. Examples will help a lot. Let's see, this is F vectors. So there's this polynomial whose coefficients are the F vectors. This just tells you how many faces there are of each dimension. And then the polynomial here, this H polynomial, has coefficients that tell you something about the size of each element in a partition, at least when the thing is partitionable. And the relationship between these two vectors is given by this remarkable identity. I mean, it's starting to look like the thing that we saw in the physics, the 1 plus t is occurring again. Okay, so now I'm going to start quoting theorems with no proofs. But here's a nice theorem. For a shellable complex, if there's one of these shellings, then the homology is 0 except possibly in the highest dimension. So that means that this thing has no one-dimensional cycles that are not boundaries. Well, that's pretty obvious. It's just a blob, right? It doesn't even have any two-dimensional homology in this particular example. It's a pretty trivial thing. Now, it does have zero-dimensional homology because it's connected. So there's a one generator with homology, but the reduced homology, you replace the 1 by 0. So that's what reduced homology is. So basically, the only homology for a shellable complex is in the highest dimension, the only possible homology. And in that example that I just gave there, the trivial example, there's not even that. But I'll give you some in a minute, some examples that are less trivial. Let's see, how are we doing here? So let's start doing some examples. If I can remember where I did them, here they are. So let's look at one-dimensional complexes. I mean, here I was drawing two-dimensional complexes with these triangles. Let's just look at one-dimensional complexes with segments. So here is a complex consisting of that segment, and that segment. And all the... Okay, so let's do a shelling of it. You ready to do a shelling? So we first start with that guy. So we get four faces we've added, the whole segment, the two endpoints, and the empty set. Then we tack on the new one, so this is our x, and we add the x in the segment, so we add two things. So that's my second element of this. And then we do the same thing for the third element. So that's the shelling of that rather dumb-looking simplicial complex, that segment. And let's see, The F vector has, let's see, there are 4 edges and, no, there are 4 vertices and 3 edges. So this thing is the F vector. And the H vector, there is 1 partition into 4 elements, and then there are 2 partitions into 2 elements. So that's what the H vector is counting. Now let's do another example. Let's look at the triangle. So here's a triangle, which is a different simplicity. This one has some topology. So 1, 2, 3. There's the shelling. So we started with a new facet, so we got a partition into 4 parts. Then we added this segment. That adds a new segment and a new vertex, so it adds 2 things. Now, this segment, we already have the vertices present. So when we add this guy, we only have to add the 1 segment. So if we look at the F vector for that one, the F vector has 3 vertices and 3 edges. The H vector has 1 partition into 4 elements, 1 partition into 2 elements, and 1 partition into 1 element. And this partition, the number of partitions into just 1 element, is the top dimensional homology. So that 1 here in the H vector is telling you that there is a one-dimensional cycle which is not the boundary of something in that simplex. So there's some non-trivial homology in that triangle. Now you can do the same thing with more complicated examples. So let's take for example this graph. By the way, every connected graph is shellable. So I don't know, what would be a shelling for this one? You can do 1, 2, 3. Now it gets a little harder. I want to add, okay, I can add this one. Four, but let's see, can I add that one? Can I do it in that order? 1, 2, 3. I can certainly do it this way, because if I want to build this segment, and if I want to avoid segment 3, I can build it by building on this vertex and making this the new x. If I want to avoid this segment, using that avoids using this segment. If I want to use this segment, then I take my new x and build it that way. So, I mean, this definition of a shelling means that you have to argue that you can always get the new edge by this device of not using something that you had before. And you can probably do 5, 6 here. I'm not going to agonize over whether that's really a shelling or not, but let's hope so. So let's see, what is the F vector for that? There are 4 vertices and 6 edges. So here is the H vector, and this 3 corresponds to the fact that the last three faces you put on, you didn't need any vertices. You just put on the edges, and that corresponds to the fact that the homology of this in dimension 1 is 3-dimensional. Now that's sort of hard to see from this picture, but if you redraw the picture like this, you can see this circuit, and then that circuit, and those are the one basis for the first homology of that graph. So that's one-dimensional complexes. 2-dimensional complexes, let's look at those. Where do I have these? Might be here. Yeah, here's a square, not very exciting, shellable. Here's the first facet, here's the second facet. There is the face polynomial. There's the Schelling polynomial. Notice that there's no constant term because there's no topology for that guy. So anyway, that's a very, very silly example. Now, what I want to do now is to try to do a Schelling in front of your eyes of a sphere. And I tried this in my office, and I hope it succeeds a second time. The wrapping of this thing is a sphere. I mean, I'm not talking about the paper inside, but just the wrapping paper outside. That's topologically a sphere. And I can make that into a simplicial complex by drawing a whole bunch of diagonal lines, like that. For each face, I draw hopefully, some consistent way, a diagonal line. I think I drew them the other way in my office, so if this doesn't work, it's going to be a catastrophe. So anyway, there is a simplicial complex. How many faces? How many two-dimensional faces do I have? I have 6 faces to this surface. So I have 12 triangles there. And I can start Schelling pretty easily. I mean, I can do here 1, 2. So I can always get to throw in the first one for 3. Then I can use this vertex to construct the second one from the first one. Then I can do 3, 4 using this new vertex and this new vertex. No problem there. 5, 6. And so that was all pretty easy. But now it gets a little harder because I start having to use vertices that I've used before. So let's see. For this one, I can build it from here by using that vertex, or I can build it from here by using that vertex. To satisfy the definition of Schelling, I have to sometimes do it one way and sometimes do it the other way. So what am I on to now? 5, 6. So 7, 8, you can do like that. Then 9, 10, and then in the end, 11. Again, you have to be careful because you can either build it from here by using that vertex, or you can build it from here by using that vertex. And to escape those legal clauses in the Schelling definition, you have to be flexible enough to say that you can do it either way. And then the last vertex here, wow, the last face here, last facet here, this last triangle, I guess that's number 12. You have all 3 of these vertices are sort of risky to use, but you can use any one of the 3 and satisfy the legal clauses for a Schelling. So I just shelled a sphere in front of your eyes. So that's sort of the recreational math part of the talk. Let's see, what did I say about this Schelling? Let's see. So this is this triangulation of the cube. Here the number of there were 8 vertices, 12 edges, 18 facets. No. Let's see. I've lost track. Oh, there's a typo here somewhere. There shouldn't be 4 terms in there. Let me not worry about that. Anyway, here's the H vector. So this corresponded to the first triangle that we threw down that just was totally out of the blue. And there were 5 that we could build up by just adding a new vertex and everything associated with it. Then we already had some stuff around in the picture, and so there were 5 more in that. And this last one was the 12th one that we added. All you needed to do is to fit in the triangle, and everything else, all the edges and vertices were already there. And so that one here corresponds to the fact that the second homology of a sphere is one-dimensional. The sphere is a closed surface that doesn't bound anything. Now you could ask, is everything shellable? Well, no, obviously not, because of all this topology. So here is an annulus. I better make it into a simplicial complex. So there's a simplicial complex, and it's not shellable. And it doesn't. The reason is that it has a first homology that's not trivial. So you can try to shell it. You can start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But then you start getting into trouble here. You want to build this new facet here, but there's no way you can do it other than by using this vertex here. And the rule is that given any preceding one, you have to be able to avoid using the vertex from the preceding one. So you're just stuck at that point. You can't shell that annulus. So anyway, that's the topology part of the talk. How am I doing on time? I'm doing okay. So now let's look at go back to the connected graphs, because that's what we started with. The connected graphs. So let's look at the case when we have 4 vertices. So how many connected graphs do you have with 4 vertices? Well, you have the complete graph. That's the biggest connected graph. You have 6 graphs where you take away one of the 6 edges. Then you have 3 graphs in this isomorphism class and 12 graphs in this isomorphism class, if I did the count right. And then you have 16 trees. So how many is that? 7, 10, 22, 26, 38. 38 connected graphs. And they're supposed to be classified by these 16 trees. So let's look at it from the point of view of the simplicial complex. So here is the face vector. There are there are 15 of these, 16 of these, 6 of these, and 1 of those. So that's where these 1, 6, 15, 16. Now, if you substitute in s minus 1 for t, you get the Schelling polynomial. And so you can see something about the sizes of our partitions in that case. There's 1 of maximal size, 3 of this intermediate size, 6 of this intermediate size, and then 6 of this 6 where all you do is plug in the last triangle. So it's actually kind of intricate topologically. So the homology this is a 2-dimensional complex. The homology has 6 generators. So there are somewhere in there 6 sort of closed surfaces that don't bound. Can you draw a picture of it? So this is the challenge I have for somebody who wants to, who has some geometrical insight, is to draw a picture of this thing. I tried to draw a picture here. So here are all the edges. There are 6 possible edges, like AC and AB. So here I put the 6 edges as these 6 vertices in the complex. Now all of these segments are in the complex. You can see by doing the counting. And almost all of the faces are in all the possible faces are in the complex. How many possible faces are there? Let's see, how many possible faces are there? We have, is it 20? Yeah, 20 possible facets, and 16 of them are in there. So I have to shade in of these triangles, 16 of these triangles, leaving 4 unshaded. Now it ought to be easy to do that with some kind of a plastic model. You take some wires and you make these wires to be these edges, and then you put in plastic, maybe different colored triangles, and you could get a good picture of this complex. Now, maybe the key to visualizing this is realizing which ones you leave out. The ones you leave out are the ones that correspond to these 4 trees, because these 4 trees have complements that are not trees. Well, these 4 are not complements of trees. So you can actually, if you want, instead sketch the 4 triangular facets that are not supposed to be shaded in. And maybe that gives you a way of visualizing. I tried to do it, but I started to get very ugly pictures and I gave up. But that's a project for someone to do. Okay. Now, getting back to matroids, it turns out these complexes that come from complements of trees satisfy this matroid property that we talked about at the beginning. And that in turn implies that they're always shellable. So that in turn implies that they're always partitionable. So now what does it mean for this complex to be a matroid? What it means is that you have all these faces here, all these two-dimensional facets, all these triangles. They're all close to each other. So they're kind of all intertwined in some very complicated way. None of them is very distant from any of the others. So it's a sort of densely arranged geometrical complex. That's the matroid property. So the conclusion is that the complex of complements of connected graphs is a matroid complex. And every matroid complex has a shelling. And in fact, it's very easy to construct a shelling. One way to do it is to arbitrarily order the vertices of the complex, of the matroid complex, then linearly order the facets with lexicographic ordering, and that gives you a shelling. So it's maybe not the only way to do it, and maybe you can get partitions without shellings, but at any rate, that works. Each shelling gives a Boolean partition, and of course, since there are many shellings, there are many ways of getting these partitions, but the H vector is an invariant of the partitions. And so there's some order in that chaos, and next time I will show you a completely different approach to classifying connected graphs by trees, which also attempts to put order into chaos, but by a different method. So that's all I have to say for today.
Questions?
So I vaguely recall something which may be equivalent to shelling. Maybe it's only necessary or sufficient, I can't remember. So which says that you order the facets, and you have to look at each facet and intersect it with the complex that you've got already.
Yeah.
And that should be pure of dimension 1 less than the original complex.
Well, that's part of the definition, but there's another legal clause that
It's equivalent.
it's equivalent. It's pure of.
Codimension 1.
Intersection is pure of codimension 1.
So that exactly explains why that 15th facet can't be added in the annulus there. Because its intersection with the previous stuff has a bit that's codimension 2.
Okay. So that's a more elegant way of explaining it. Next time around. Thank you. I apologize to the experts on this stuff.
Oh, it's great, Bill. I enjoyed it. I'm looking forward to next week.
Next week, a different story.
Thank Bill again.